Okay, so this is the Unit 3, Day 3 concavity and the second derivative test. So basically our goal for this unit is to kind of see what the derivative or the second derivative can tell us about the behavior of the original function f of x. So right here I have a chart, and it kind of summarizes what the second derivative or first derivative will tell you about the original. So last class we used the first derivative test, and one of the things we did was drew a sign chart, and we said, well, say you took the first derivative and say it was positive and then negative and then positive again. Well, we said that if we knew that that happened, then we knew that the original function was increasing, then decreasing, then increasing. And so then we were able to say, well, whatever this critical value was here, there was a max because we went from increasing to decreasing, a relative max, and then at whatever this critical value was here, since we went from decreasing to increase, there was a relative min there. And that's kind of exactly what this chart is saying. So this chart's saying, well, if the derivative is positive, we knew the original function was increasing. If the derivative was negative, we knew that the original function was decreasing. So this chart, I know there's some students that choose to just kind of memorize the chart and go from there, but I always like to kind of bring it back to my sign chart because that's what I'm most comfortable with. Okay, so just to review what we did last class, I'll start off with a first derivative test. And so in this first example, we're given a polynomial here, and find the intervals on which the function is increasing or decreasing. So if we're trying to find intervals of increasing and decreasing, that's a first derivative test. And the first derivative test says, well, you take a derivative, and we want to figure out where that derivative equals 0 or is undefined. So the derivative here is a simple power rule. So once you take the derivative there, we want to figure out where that derivative is 0 or undefined. I don't need to worry about this derivative being undefined anywhere. So I'm just going to take the derivative and set it equal to 0. Okay. So I'm going to factor out a 15x squared, and that would leave me with an x squared minus 1 equals 0. And here, that's the difference of two squares. You could factor that into x plus 1, x minus 1 if you wanted to, but either way, you're going to get x equals 0, x equals 1, and x equals negative 1 as your critical values. So again, those are called your critical values or critical numbers, and that's nothing new. We did that last class. And so now I'm going to go and take those critical values and I put them on a number line. Recall that when you put your values on the number line, they do need to be in order. So negative 1 needs to come first, and then we have 0, and then we have 1. Okay? And I always make myself a note that I'm plugging into the derivative, and it's telling me information about the original. So then here was the point that you had to plug in. So say you plugged in a number to the left of negative 1 into the derivative, okay? And you can plug into either form. I actually think plugging it over here is probably easier. So if I plug in a negative 2, and sometimes you'll see I'll write like just a little negative 2 on there, and that's just a little note to let me know what I plugged in. So if I plug in a negative 2 and squared, I get a positive here, and then a negative 2 squared, that's going to be 4 minus 1 is positive, so you have a positive times a positive, so that's a positive. And again, what does that tell me? It tells me the original function is increasing. And so then I plug in a number in between there, so a number like negative 1/2. So again, I just kind of note that for myself. So when I plug in a negative 1/2, I get a positive on the outside, but on the inside here, negative 1/2 is squared as a fourth. So a fourth minus 1, that's going to be a negative. So you have a positive times a negative, which will be a negative. And then when I plug in positive 1/2, again, I get a positive here, but I'm going to have a negative there, so you get a positive times a negative, which is a negative. This is a great example of one that does not alternate. I know a lot of people say, well, can't I just say, oh, plus minus, plus minus, plus minus? No, you may not. Notice this one does not alternate in sign like they do many of the times, but definitely not always. And, oh, and I plugged in a half there. And here I'm just going to plug in the number 2. So 2 squared, that's positive, and this piece will be positive. So I've got this. So again, that tells me that my original was increasing, then decreasing. Then the derivative was 0, but it was still decreasing afterwards, so it might have just kind of had a flat spot, and then it started to increase again at the end. So that's my first derivative test. Remember that the sign chart is not enough to get full credit on the AP exam. You need to make a concluding statement. So my concluding statement would be something like f of x is increasing on the interval negative infinity to negative 1, union, and then it's increasing again from positive 1 to infinity. Okay, and again, that's because the derivative was greater than 0, or you could say the derivative was positive. And then the next concluding statement I can make is that f of x is decreasing on the interval negative 1 to 0, union 0 to 1. I like to keep those separate just so that you know something was going on at 0, right? Like the derivative was 0 at 0, so I like to keep those separate there. And again, my justification there is because the derivative was negative or less than 0. So there's my concluding statement, and again, that's exactly what we did last class. So there's kind of a review. Now we get into what we call the second derivative test. So the second derivative test means we're going to examine the second derivative and see what does that tell us about the original function. So I have that chart up there, but let's see what we can, turn it into more of a sign chart instead of just some chart that we memorized. Okay, so here's a key word here, is this points of inflection. So a point of inflection is where you change concavity. So to think of concavity, you may want to kind of revisit a parabola from Algebra 2. So recall that if you have a parabola that's like this, we call this concave up, okay? And if you have a parabola opening downwards, we say that that's concave down. So the second derivative test is going to be able to tell us about the concavity of the original function. So that's kind of what we use it for. So it says, find the points of inflection, and again, that means where does it change concavity, as well as the intervals on which the original is concave up or concave down. So we had a little review on what it means to be concave up or concave down. And again, whenever I see this, you should be thinking second derivative test. Okay. So the second derivative test, as you can imagine, I have to take the derivative of the derivative, and we indicate that with the double prime there. So the derivative of this up here, 4 times 15, that's going to be 60, x cubed, and then minus 30x. So there's my second derivative. And as you may suspect, we're going to figure out where this derivative equals 0 or where this derivative does not exist. So in this case, I don't need to worry about the derivative not existing because there's no restrictions on x there, but I can set that derivative equal to 0. So I'm going to figure out where that derivative equals 0. So I'm going to factor out a 30x, and that'll leave me with 2x squared minus 1 equals 0. And again, it's set your derivative equal to 0 or does not exist. And again, I didn't need to worry about that in this problem. So when I set this equal to 0, I get x equals 0. And if I set this piece equal to 0, I'm going to get, let's see, that'd be 2x squared equals 1. So x squared is a half. So that must mean that x equals plus or minus 1 over the square root of 2. Okay. And these, now, just like up here, we called them critical values, okay? Down here, these are your possible, and I definitely want you to underline that word possible points, or really they're possible x values of inflection. Okay? And it's really important here that you realize that they are possible. So it is only a point of inflection if you actually change concavity. So just like up here how the sign chart doesn't always alternate, okay, it's only going to be a point of inflection or an x value of inflection if it actually changes concavity there. So these are just possible points of inflection. And now I'm going to do a sign chart. So I do the sign chart very similar thing. And this time I'm going to label this f double prime. And I want to know what it tells me about the original. So that's why I'm very particular, and I always make sure I label so that I pay attention to what I'm doing. And I put those possible x values of inflection on there. So I have negative 1 over square root of 2 and 0 and positive 1 over square root 2 there, right on my sign chart. And then I'm going to be plugging in. So just like I did before, I'm going to take a number to the left of this value here, and I'm plugging it into the derivative, and that's why I label it. It really helps me pay attention to what I'm doing. So when I plug in a negative 2, I'm going to get a negative over here, and then I'm going to get a positive there. So a negative times a positive is negative. And then when I plug in a number in between there, okay, you have to be careful there. So you might need to know, your square root of 2, you know it's going to be less than 2 and bigger than 1, okay? So 1 divided by that, right, you're going to have a negative. So maybe you pick something just really, really tiny, like maybe just a negative 0.01. So that's going to be a negative, and this is going to be a negative, because negative 0.01 squared is really little, right? And if you subtract 1, that's going to be negative. So you have a negative with a negative, so that's going to give you a positive there. Very similarly over here, only you're going to have a positive times a negative in there would be a negative. And if you plug in a number like a 2, that'll be positive, so you get a positive out there. Okay, so what does this tell me? Well, if it's negative, that means you're concave down. So it's looking like this, okay? And if it's positive, and when I say it, I shouldn't say it. When your second derivative yields a positive result, that tells you the original is concave up. And so you can fill those in like so. Okay, once you have this, you can then write your concluding statement. Okay, so here I would say, you could say f of x is concave up. Or you could say on, so it's concave up between those two. So that's negative 1 over square root of 2 to 0 union, and then it's concave up again at 1 over square root of 2 to infinity, because the second derivative is positive. And then we can say that the original is concave down. From, let's see, it's concave down from negative infinity until negative 1 over square root of 2, and then union from 0 to 1 over square root of 2 there. Okay, so what does that mean? Because you actually changed concavity at all of those possible points of inflection, you have points of inflection. Okay, so points of inflection, I'm going to abbreviate with POI. Points of inflection at x equals plus and minus 1 over square root of 2 and x equals 0. So because they actually all changed, those are all points of inflection, or all x values of inflection. And that is your second derivative test. Okay, this is a continuation of the Unit 3, Day 3 second derivative test. So I wanted to kind of walk through this one with you. So it says find the points of inflection of g of x, as well as the intervals over which the function is concave up or concave down. So this concave up or concave down is my clue that I want to use the second derivative test. So for the second derivative test, we obviously need to take the first derivative first. So I took that first derivative using just a power rule. Now, you could, if this also asked you for where the interval was increasing and decreasing, then I'd have to set this equal to 0 and do all that. But since it only asked me about being concave up or concave down, I just kind of, use my first derivative, and then I go straight to my second derivative. So now I'm taking the derivative of this here to get to here. And we're trying to figure out where that second derivative does not exist, or where that second derivative equals 0. In this case, I don't need to worry about anywhere where it doesn't exist. There's no restrictions on x there. So what I'm trying to do is take the second derivative, set it equal to 0. I factored out a 20x squared, and so I get to here, and that gives me these possible x values of inflection. So remember, they're only possible x values of inflection because it is only a true point of inflection if the original changes concavity. So I make my sign chart, and again, this time I label it g double prime because I'm plugging into the second derivative, and it's telling me information about the first. So when I plug in a number like -1 into my second derivative, I'm going to get a positive multiplied by a negative, so I get a negative. Okay, and then when I plug in a number like 1, I get a positive multiplied by a negative, so that is a negative. And then when I plug in a number like a 4, I get a positive times a positive, which is positive. So what does that tell me? It tells me that g was concave down, and then it was concave down some more, and then finally at x equals 3, it switched to being concave up. So notice that the only point of inflection is at x equals 3. So this actually is not a point of inflection. There was something going on in the second derivative there, but it didn't actually change concavity. So the only true point of inflection is x equals 3. So a question on this might say something like, how many points of inflection does this have? So the answer to that would be 1. So kind of my conclusion here, we'd say g of x is concave up on the interval 3 to infinity because the derivative there is positive. And we say g of x is concave down from negative infinity to 0 union 0 to 3 because the derivative there is less than 0. So we have that being negative. And there is a POI, a point of inflection, at x equals 3. And did I answer the full question? Ooh, it said find the point or points of inflection. So I just said there was a point of inflection at x equals 3. To get the actual point, if they want the actual point, I need to take that 3 and plug it back into the original. So when you take that 3 and you plug it back into the original, I got a negative 154. So there's my answer. I had to kind of squeeze it in there. So just be careful that you're answering the full question here. It didn't say, you know, if there was a point of inflection. It actually wanted to know what the point of inflection was. So I had to take this 3 and plug it back into the original to get the actual point of inflection. So my point of inflection is at 3, negative 154. Okay, so that about sums that problem up. And we could take a look now at this calculator example, and I wanted to bring your attention, this should have been given information. I had forgotten to do that. So just pretend like this was typed in there, that they gave us an interval. And again, you always want intervals with trig because those trig functions tend to oscillate, and you'd be here a very long time if you didn't have an interval. So we're just going to pretend like that was there. I had printed this before I made that change. Okay. So in example 2 here, it says for f of x equals this whole thing, find the points of inflection as well as the intervals over which the function is concave up or concave down. Again, this is what tells me I'm thinking the second derivative test. Notice though that I made this one a calculator question, but I'm still going to do it as if I was doing the second derivative. I'll have you practice taking the derivative here, but keep in mind, how would they make this a better calculator question? They would probably give you the second derivative and then ask you to analyze it, because clearly here, if I really wanted to, I could just type this original in there and take a look at where it's concave up or concave down. But for right now, I just want to kind of practice taking some derivatives. So I put this one on there, and I would take this derivative. And that's going to be, all right, the derivative of that is 0. Then I'm going to get a negative 5 plus 4x. And then over here, you're going to have kind of a chain rule and trig. So the derivative of negative cosine is going to be positive sine. So it'll be positive sine of 3x, then chain rule times the derivative of the inside. So you'd get a 3, and I'll write it like that. And then I'm going to take that second derivative. Okay, so the derivative of this goes away. Then I'm going to be left with a 4, and the derivative of sine is cosine. So it'd be plus 3 cosine of 3x. Again, chain rule times that 3, so you could change that to a 9, and I'll just write a 3 there. Okay. Okay, so what am I trying to do? I'm trying to figure out where this thing equals 0 or does not exist. So basically what we're going to do is we're going to have 4 plus 9 cosine 3x, and I want to figure out where that thing equals 0. So what I would do is I would take this and I would put this right into my y1 on my calculator. Okay. And then you have two choices. You can either put 0 into your y2 and then do second calc intersect, or you could just find the zeros. So basically what I'm going to do here, so I have just our calculator. I'm going to hit y equals, and I just typed in 4 plus 9 cosine 3x. I'm in radian mode. And I would recommend maybe hitting zoom, and then choice 7 there says trig. So if you hit zoom 7, you're going to get this. And it'll quickly become apparent why we need to take a look at a very specific interval. So I'm going to adjust my window with my interval. So I'm going to change my interval from -1 to 2. And I saw that it was creeping up. So I don't know, maybe I adjust this to -15 to 15. And I'll just kind of graph that and see if that kind of cleans it up. Oh, that seems to do a nice job. And again, I don't really need to see this peak or this valley here. What I'm really concerned about is where the second derivative is positive and where it's negative. So you'll see here I have this negative part here before it turns positive, and then I have negative again, and then it's positive there. So really what I'm interested in is this point, and this point right there on my calculators. So you can either do second calc zeros, or you could do second calc intersect, but if you do second calc intersect, you have to hit y equals and also graph the line y equals 0. So make sure I'm answering the question here. So it says find the intervals over which it's concave up or down. So it does want everything. So to get those over there, I'm going to kind of start on the left, and I'm just arrowing over till I get to the left of it. Notice that my calculator says left bound question mark, so that's telling me go to the left of the point you're looking at. So again, the point that I'm trying to tackle is right there. So I go to the left of it and I hit enter. Notice your calculator changes to say right bound, so that means you need to move your calculator to kind of trace it so that it goes to the right of the point you're examining. Hit enter, and your calculator should give you these two cursors up here. Basically, that's your calculator saying, you want me to figure out where you cross the x-axis between these two things, right? So if you'll notice, the point I'm looking for is right between there, so I'm good, and that's when you hit enter the final time, and your calculator spits back that value. And you're going to repeat that process, so you probably want to jot that number down, negative 0.677. And then I'm going to do the same thing, second calc, I'm going to do the zeros. So it says go to the left. So now I need to kind of cruise way over until I get to the left of that second point. So I don't know, that's to the left of it. I hit enter. And then I go to the right of it. I hit enter. Notice my calculator says, you want me to figure out where you cross the x-axis between here, right? And I say, yep. I hit enter, and it gives me the second one. And then you just repeat that process for the third. So when I go to do my sign chart, again, I always kind of make a note of what I'm looking at. So my second derivative, and it tells me information about my original. That first one that we hit was at negative 0.677. Then there was another one at 0.677. And then that last one, if you went and did it, I got 1.417. Okay, so there's my sign chart. And, oh, I guess these should actually be between -1 and, I shouldn't have an arrow there because we kind of truncated our interval there so that we were just looking at that piece. And what did we notice? Well, again, if you kind of looked back to the graph there, well, before this point, it was negative, then it was positive, then the second derivative was negative again, and then it ended up as positive. Okay, so I've got that. What does that tell me about the original? Well, it was concave down, then concave up, then concave down, and then concave up between those. And then I don't like the way that looked. There we go. Okay. So we can write our concluding statements there. Notice it did change concavity at all three of those possible points of inflection, or those possible x values of inflection. So these are actually all POIs. And so I can say that this thing was, let's see, I shouldn't say this thing. F of x was concave up on the interval negative 0.677 to 0.677, union, and then from 1.417 to 2. Okay. And then why was that? That is because the second derivative was positive, so greater than 0. And my other concluding statement that I can make was that f of x concave down on the others. So it was concave down from negative 1 to negative 0.677, union 0.677 to 1.417. Close that up. And that's because the second derivative was less than 0. It was negative. And so I have, and let me see if I'm answering the full question. Find the points. So if it asks you for the points, not just where a point of inflection occurs, you actually need to go and get that point. So I would say POIs at, and now I'm going to have negative 0.677, comma, I'm going to have to go get that y value, and then going to be there. Again, I'm going to have to go get that y value, and the last one was 1 point, and then I'm going to have to go get that y value. Okay, to get those y values, there's a couple different ways you can do it. One option is you could go back and clear that out, and that was kind of bad there because I wrote on my calculator screen. Okay, you could type in the original, okay? If you put this original into your y equals, and then you could do second calc value and do it. So maybe that's how I'll do it, because there's 3 of them. So all I'm doing is typing in the original, so minus cosine, 3x, make sure it looks okay in there, and then I can graph that. And it's going to take a second. You could tell it's kind of concave. You can tell the concavity kind of switching there. And then I'm going to do second, calc, and then choice 1 is value. Now I should be careful here because technically I'm using this rounded answer. I should be using my whole decimal. But let's see, negative 0.677. So if I do that, I get 12.746. So I record that one there. And then I could do second calc value. And then I wanted to do 0.677. And I hit enter. And I get 5.976 there. And then if you do second calc value with the last one, you get 5.376. And that's that. Okay, just a couple more examples from the Unit 3, Day 3 notes over the second derivative test. I wanted to talk about an example where they give you the graph. So a lot of times on the exam what they'll do is they'll give you a graph and they'll ask you to do some function analysis. What I really want you to be careful of is what you are looking at. So in this problem, it says the graph of f double prime is given below. So you're looking at the graph of the second derivative. So determine the open intervals over which f is concave up or concave down. So they're asking you to determine information about the original function given the graph of its derivative. So again, I always try to relate these types of things to sign charts. So for me, I'm always like, okay, well, my second derivative test, if I want to know information about the original, what I care about is where that second derivative is positive or negative. So in here, I would say that this, in this example, the second derivative starts off as being positive, right? So for this section right here, okay, it is positive. Let me actually do that in yellow. Okay, so it starts off positive. Then it dips below the x-axis for this part here. So then it goes to negative. And that changes at -4. And then it goes to being positive again at -2, and it stays positive until it hits 3. So we'll say that it goes positive, and then again, that change from negative to positive here occurred at -2. And then at 3, it touches there, but then it still stays positive. So we've got something that looks like that. Okay, so if I'm interpreting this sign chart, to me, that tells me that it's concave down just where that is negative, and concave up here, and here, and here. So for this problem, what I'd really like you to kind of see is they could ask you about 3 specifically, if 3 is a point of inflection. Now remember, an x value is only a point of inflection if it actually changes concavity. So in this problem, the point of inflection would be at x equals -4, and again at x equals -2. X equals 3 is not a point of inflection because it did not actually change concavity. So kind of some conclusions here. We know that f of x is concave up. Well, it's concave up when the derivative, okay, is greater than 0, when it's positive, and it's concave down when, the second derivative, when the second derivative is less than 0. So in this case, it's concave up. So I guess I'll fit it underneath there. So we're looking at being concave up from -infinity, okay, until, what is that, -4, union, and then it's concave up again from -2 to 3, union 3 to infinity. And I just have that union there because there is something going on at 3, right? Like my second derivative does hit 0 there, but it just kind of bounces and then it's still concave up there. And so it's concave down when the derivative is negative, so that's going to be just this part. So that is from -4 to -2. So that's my only interval of concave down. Okay? All right, so then we've got this problem here. So again, paying very close attention. This time I'm given the graph of the first derivative. So the first derivative is going to give me information about the original. So normally, and let me look kind of here, what is it asking for? It's asking for points of inflection, and it's giving me specific points. So if I'm given the graph of the first derivative, I can tell you information about if f is increasing or decreasing, but it's not asking me about that. It's asking me about points of inflection, which means it's giving me the graph of the first derivative, but it's actually asking me questions about the second derivative. So you have to think about what's the relationship between the first derivative and the second derivative. Well, it's really asking you about you could think about it as the slope. So if you didn't want to memorize that chart from the very beginning of the notes, you could just think of it as the second derivative is the slope. So what can you tell me about the slope over this section? Well, the slope over that section is a positive slope. And then it switches to a negative slope. Okay? So where those points are going to change. So here I'm positive, positive, positive slopes. Then I start getting a negative slope. Then I start getting a positive slope. Then I start getting a negative slope, positive slope, right? Negative. So it becomes all those like peaks and valleys there are going to be pretty important. So a point of inflection when your original goes from concave up to concave down or concave down to concave up. But what does that actually mean? It means that there's a point of inflection when the derivative goes from increasing to decreasing or decreasing to increasing. So in this case, there's going to be 6 points of inflection. So 1, 2, 3, 4, 5, 6 points of inflection. So POIs occur when, and again, there's kind of two ways that you can think of it. I think of it as when the derivative, okay, when the derivative goes from increasing to decreasing, or from decreasing to increasing, okay? And again, you could think of it as when the original goes from concave up to concave down. So here there are 6 POIs. Okay. All right, and the last part there. So the point 3,5 is on the graph of y equals f of x. Find the equation of the tangent line to y equals f of x at that point. Okay, so what's another way to interpret this? Okay, well, what is the derivative at 3? Well, I have a graph of the derivative. So would you agree that the derivative at 3 is 2? So the derivative at x equals 3 equals 2, right? So the derivative at 3 equals 2. So that was my x value, so I did that. And so then I've got that trusty formula, my point slope, y minus y1 equals m, parentheses x minus x1. So the derivative is the slope. So I guess this 2 is my slope, so that goes there. And then I've got the point that they provided me. So I've got y minus y1 equals 2 parentheses x minus x1. And again, there's your safe stop. If you wanted to go on and solve, especially if the problem, if it was a y equals, let's see, that'd be a 2x. You get minus 6 plus 5. So that would be a negative 1 there. All right, and that is some extra examples on the day 3 notes. Stay tuned for the homework. Okay, this is the homework for Unit 3, Day 3. It is on concavity and the second derivative test. So the goal of the second derivative test is we're going to again do a sign chart, but really it's going to tell us if it is concave, if the original function is concave up or concave down. So here's an example of concave up, here's an example of concave down, and that also tells us if there is a maximum or a minimum at that possible point of inflection, okay? So what we want to do here, kind of scooch this up a little bit. Okay, so for this first example, it's dealing with trig. So again, we have an interval there. We are only asked in the directions to find the point or points of inflection as well as the intervals over which it's concave up or concave down. So it is not asking us about intervals of increasing and decreasing, and because it's not asking us about those, then I can just go ahead like right to the second derivative. So I'm going to take the first derivative, and then normally we could pause there and then we'd be able to, talk about increasing and decreasing. But since it's only asking about the concavity, I'm just going to take that first derivative, and then I'm just going to take the derivative of that. Okay, the derivative of sine is cos. Cos is negative sine. And so that'll be a minus cosine there. Okay, so now I took the derivative, or the second derivative, and now I need to figure out where the second derivative equals 0 or where the second derivative does not exist. I don't need to worry about this not existing anywhere because it's sine and cos, so it's bounded. I'm not dividing by 0 or anything like that. But I can figure out where that equals 0. So figuring out why the second derivative, okay, equals 0. So if I set this thing equal to 0, so negative sine x minus cos x, if I set that equal to 0, basically I can move one of those over. It doesn't really matter which one. So I'm just going to say that I conclude that negative sine x equals cosine of x. And you're like, well, I kind of get stuck there, right? Well, not exactly. Think of on your unit circle where are sine x and cos x the same, and then we'll just need to make sure that one of them is going to be negative. So if I go to a unit circle here, notice this unit circle isn't rationalized, so I'm going to use this one instead. So notice that your pi over 4 is your x value and y values are the same, aka sine and cos are the same, but we really want them to be the same, but one is negative. So that would be in quadrant 2 and also again in quadrant 4. So it's going to be the 7 pi over 4 and 3 pi over 4. is what we're going for. And so I'm going to say that x equals, that was 3 pi over 4, and also 7 pi over 4 is where that's true. Now these are possible, okay? It's not for sure. There are possible POIs. And really there are possible x values of inflection, but I'm just going to call them possible points of inflection. So from here I do need to draw a sign chart. So I draw a sign chart. And this time I'm looking at the behavior of the derivative, the second derivative, and it is going to tell me the behavior about the function. I put my possible critical points on there, and 7 pi over 4. And again, this is bounded, so really instead of having arrows here, I should really have end marks because, you know, I'm bounded by 0 and by 2 pi, so I shouldn't really have arrows there. And so I'm plugging in. So when I plug in something in between 0 and 3 pi over 2, I don't know, a good candidate might be a pi over 2. So I'm plugging that into the second derivative. So if you plug that into the second derivative, so pi over 2, sine of pi over 2 is 1, but it's going to be negative, so I've got a negative 1. And the cosine there is going to be a big old 0, so it's going to be negative, because negative 1 minus 0 is negative. Then plug in something between, so a good candidate in between there would be something like pi. So when I plug in pi, sine of pi is 0, cosine there is going to be a negative, but it's minus a negative, so that's a positive. And then when I plug in, I don't know, something like 11 pi over 6, or doesn't really matter, just anything in between there, I'm going to get, that's going to be a negative. Okay. So that tells me that since this is the second derivative is negative, that tells me it's concave down here. Tells me the original is going to be concave up there and concave down again between those. So my conclusion would be that f is concave up on the interval 3 pi over 4 to 7 pi over 4. And I can conclude that f is concave down, and then I'm going to have to do a union on these two because there's going to be 2, from 0 to 3 pi over 4, union 7 pi over 4 to 0. Okay, so I can conclude where it's concave up and concave down, and since the concavity did switch, those are indeed points of inflection. So I have a point of inflection at 3 pi over 4 is 0, and again, that y value is obtained by taking this x value and plugging it into the original, okay, and there. All right, and number 4, again, we're going to skip right to the second derivative because it's not asking about increasing or decreasing intervals, it's just asking me about concavity, so I take the first derivative, then I take the derivative of that, and my goal is to take that second derivative and set it equal to 0 or where it does not exist, but in this example, I don't need to worry about the derivative not existing. So all I need to do is set that equal to 0. So if I set this equal to 0, I end up getting x equals negative positive 2. So again, this is a possible, okay, x value of inflection. So it's a possible POI. To determine if it is truly one, I have to do a sign chart. So my sign chart, again, I put the second derivative there, and it's going to tell me the behavior about the original. I only have one possible POI there, so I just put a 2. I plug in a number like 0 into the second derivative, and that'll give me a positive, because it'll be 0 plus 12 is positive. Plug in a number to the right, like a 3, that'll be negative 18, plus 12 is going to be negative. So that tells me here it's concave up, and over here it'll be concave down. And so it is asking me that I can say that h is concave up on the interval negative infinity to 2, and h is concave down on the interval that'll be 2 to infinity. So I have that. So you could say you do indeed have a point of inflection at 2. So you could say POI at 2, comma, to get that y value, you would take this 2 and plug it in there. So you're going to have a -8. So yeah, -8 plus 24 minus 5 gives you 11. So we have that. Okay, moving on to the second, the back there of the worksheet, the second half. So it says find all relative extrema, use the second derivative test where applicable. So remember, one of the things we can use the second derivative test for is to also find the extrema. It basically says you take the first derivative, you set it equal to 0 to get those critical values. Then you take those critical values, so that's what's happening here. Take the first derivative, you get the critical values. You take those critical values and you plug them into the second derivative. So you kind of hold on to these, you go back and take the second derivative, and you plug those critical values back in. And when you plug those back in, you don't care so much about the actual number. You only care if the number is positive or negative. If it's negative, that means it's concave down, so you'll have a maximum. If when you plug in you get a positive, that means you're concave up, so you're also going to have a minimum there. Okay, so for number 5, what I did is I took the first derivative and I set it equal to 0. So by factoring, you can go ahead and get those critical values. Then I took the second derivative, so I took the derivative of this here. And then I need to take these critical values and plug them into the second derivative. So when I plug those into the second derivative, when I plug in 4, that's going to give me a positive 6, right? So that, what I really care about is that it's positive. So that means that it's concave up. And because it's concave up, that means that there's going to be a minimum at 4. So that we could say that there is a minimum at x equals 4. Then when you plug in a -2, so when you plug in a -2 into the second derivative, that'll be a -4 minus 2 is going to give you a -6. Again, I don't care about the 6 so much. I really care that it is negative. So that means I'm going to be concave down, which implies that there will be a maximum at x equals -2. So we have that there. Okay, in the next one, we are trying to figure out about the graph of the continuous function is given below. Now notice they give me the graph of the derivative, and they are asking me about questions about the original. Okay, so here it says find all the values of x on this interval. Notice that -6 and 3 are not included in there, for which f has a horizontal tangent line. So you should know that horizontal tangent line, well, horizontal tangent line means that your derivative equals 0. That's what that means. So this occurs when the derivative equals 0. Well, looking at the graph, where does that occur? Well, here the derivative equals 0 right here, here, and here, right? And so which of those are we going to steal? We're going to use -2 and 2. Why aren't we using -6? Because it's not included. So I would say that there is a horizontal tangent line at x equals -2 and x equals +2. And then it asks you furthermore, determine whether it has a relative max or min or neither at these values. Well, what you need to know is that we're really concerned about whether the derivative is going from positive to negative. That's when you get max and mins, or when you go from positive to negative or negative to positive. Okay, so to determine if you have a relative max or min at -2, you're concerned if the derivative goes from positive to negative. Well, if you look at -2, your derivative is positive and then positive. So there's no relative max or min at -2. So I'll just say at x equals -2, the derivative goes from positive to positive. So no max or min. Okay, so I don't need to worry about that one. Now let's examine what's going on at x equals +2. Well, at x equals +2, the derivative goes from positive to negative. Okay, the derivative goes from positive to negative. So that tells you that there's going to be a maximum, because that implies that your original, right? Think about what a sign chart would be. If if your derivative, right, if you were just kind of picturing a sign chart, if your derivative went from positive to negative, that would imply that your function is going from increasing to decreasing. So that tells you that f goes from increasing to decreasing, and if you go from increasing to decreasing, that means there is a relative maximum there. Perfect. Okay, and then the last part here, so find all values of x on the interval for it has a point of inflection. So point of inflection, that's going to occur when you go from concave down to concave up, or concave up to concave down to concave up, or vice versa. Or really when your derivative, okay, so a POI, when your derivative goes from increasing to decreasing, right? So where does that occur? Well, where does your derivative go from increasing to decreasing? Looks like right here. And here it goes from decreasing to increasing, so right there. And we have it increasing, decreasing at 0 as well, and then it's decreasing, decreasing there. So we are going to say that happens at -4, at -2, and at 0. And that is your homework for the day.